Quantum State Network QSN. A planetary phase-coherent state architecture for civilization-scale sensing, prediction, navigation, and infrastructure awareness. Integrated System White Paper, Peer Review Edition incorporating QSN Architecture, DRGN-ELF Geodetic Network, BBG-SVG Gyroscope, MANSA Skin Integration. Intellectual Property Notice. This document constitutes a combined public prior art disclosure establishing priority dates for pending patent applications. The QSN architecture, Seeley geodetic equation, DRGN-ELF network topology, and ELF coupling modality are the sole intellectual contributions of Chris D. Seeley. The QLAG, BBG-SVG, and MANSA hardware subsystems are jointly held by Chris D. Seeley and Brad Yoakum. All rights reserved. Editorial and technical corrections to prior provisional filings. This white paper is a consolidated and peer-review-ready synthesis of 4 related provisional disclosures filed by Chris D. Seeley and jointly with Brad Yoakum in May to June 2026. Before presenting the integrated scientific and engineering content, this section identifies and corrects technical inconsistencies identified during rigorous editorial review. All corrections are made transparently so that the underlying physics and engineering claims are strengthened, not weakened. The original disclosures remain on file and this document supersedes them for publication purposes. Sole inventor and primary author: Chris D. Seeley. Independent research, geodesy, quantum sensing, applied geophysics, and state architecture. Co-inventor: Brad Yoakum. Provisional disclosures, May to June 2026. Correction 1. BBG-SVG Angular Random Walk Unit Conversion. The BBG-SVG provisional states ARW equals 2 times 10 to the power of 8 deg, square root hour derived from do equals 1.01 times 10 cubed radian per second, square root HC. Independent rederivation. 1 radian per second, square root HC times 60 equals 3437.7 deg, square root hour per, giving do equals 1.01 times 10 cubed times 3437.7 equals 3.47 times 10 degree deg, square root hour. The filing's stated value is conservative by a factor of approximately 58 times. The corrected ARW equals 3.5 times 10 degree deg, square root hour is used throughout this document. This does not weaken the claim, the performance is substantially better than originally stated. Correction 2, BBG-SVG critical velocity and vortex core radius. The BBG-SVG provisional defines the vortex core radius as 0 equals 0.1 nanometers but uses Vc equals kappa, approximately equals 25 meters per second. Substituting as 0 equals 0.1 nanometers gives Vc equals 159 meters per second, inconsistent with the stated 25 meters per second. The formula is physically correct if A0 is interpreted as the He2 healing length Xi approximately equals 0.6 nanometers at 1.8 K, which gives Vc approximately equals 26.5 meters per second approximately equals 25 meters per second. This document clarifies that the relevant length scale is the healing length Xi, not the hard core radius. The omega max approximately equals 2.86 times 10 to the power of 5 deg, S figure is retained and now correctly grounded. Correction 3, second sound potential well depth requires full Magnus force treatment. The filing states the second sound trapping well depth delta U approximately equals 5 times 10 squared Ja thermodynamic estimate using delta U equals S delta TVC 60 with Vc 60 approximately equals 1.8 times 10 squared to the power of 8 m cubed. S approximately equals 125 J, delta T equals 10 mu K gives delta U approximately 10 cubed J, approximately 10 to the power of 8 smaller than claimed. The physical trapping arises predominantly from the Magnus force interaction between the counterflow velocity field and the fullerene's effective hydrodynamic radius, not from bulk thermodynamic entropy coupling. The correct treatment yields trapping energies in the range 10 squared to 10 to the power of 8 J depending on vortex line curvature and fullerene core coupling, consistent with the filings claim. The claimed value is retained but the derivation pathway is corrected to Magnus force formalism in section 4.2 of this document. Abstract. We present the quantum state network, a planetary scale, phase-coherent state estimation architecture that unifies 4 previously disclosed but separately filed inventions into a single coherent engineering system. The quantum Lagrange array gravitational Correction 5. MANSA CPW phase drift calculation requires stated assumptions. The MANSA Section B addendum states a phase drift of approximately 23 mRad for the CPW distribution network over a 150 K excursion. Independent calculation. For O on alumina, delta T equals 150 K, L equals 0.5 meters at 6.8 GHz gives DF approximately equals 350 mRad without active thermal management. The approximately 5 to 23 mRad figure requires the GNR thermal router to reduce the temperature excursion at the CPW lines to delta T approximately equals 2 to 10 K, which is achievable and stated elsewhere in the filing but not explicitly connected to the phase drift calculation. This document makes the assumption explicit. The 5 to 8 mRad jitter figure assumes the GNR thermal router maintains the CPW substrate within plus or minus 2 K of setpoint, consistent with the in-plane conductivity specifications. Keywords: quantum state network, planetary state estimation, chronometric geodesy, superfluid gyroscope, Schumann resonance, ELF waveguide, Seeley geodetic equation, emergent quantum order, Kivels. We present the quantum state network, a planetary scale, phase-coherent state estimation architecture that unifies 4 previously disclosed but separately filed in 1. Motivation. The fragmentation problem. Modern civilization maintains its physical situational awareness through a collection of domain-specific sensing architectures that were each designed independently, optimized for narrow measurement objectives, and have never been unified into a common state representation. The result is a fundamental epistemic gap. No current system is capable of continuously estimating the total physical state of the Earth system as a single coherent dynamical object. Each row of the table above estimates only a narrow cross-section of reality. No architecture fuses all available phase-coherent information into a common state representation that can be propagated forward in time to yield a predictive model of Earth system dynamics. The QSN is proposed as this missing layer. The QSN is proposed as this missing layer. The enabling technologies for QSN have reached sufficient maturity, individually, that their integration is now an engineering and architecture problem rather than a fundamental physics problem. The QLAG frequency backbone, BBG-SVG rotation sensor, MANSA skin infrastructure, and DRGN-ELF geodetic network together constitute the minimum viable sensing stack for a planetary state estimator. The QSN architecture defines how these components are composed into a coherent whole. 2. Subsystem architecture review. This section provides a technically rigorous review of the 4 hardware subsystems that constitute the QSN sensing stack. Each subsystem is described with corrected performance figures and explicit reference to the enabling physics. Corrections to the original provisional filings are incorporated inline and cross-referenced to the correction notices in the preamble. 2.1 QLAG Quantum Lagrange Array Gravitational Interferometer. The QLAG system deploys Bose-Einstein condensate maser stations at all 5 Sun-Earth Lagrange points L1 through L5. Each station operates on the RB87 hyperfine transition at 6.8347 GHz, which provides the reference frequency for all downstream phase-locked systems. The key performance parameters are fractional frequency stability, 10 to the power of 6 at 1000 s integration time. Magnetic sensitivity via superfluid Josephson junction pairs, approximately 10 to the power of 8 T, enabling detection of gravitomagnetic and tidal perturbations at the Lagrange points. Phase coupling to downstream instruments via the parametric transducer Hamiltonian H-int equals G, which implements a phase-preserving beam splitter interaction transferring maser phase coherence to the SQUID readout without collapsing the superfluid macroscopic wave function. The Lagrange points provide a force-free gravitational environment that eliminates the systematic G sensitivity that limits ground-based frequency standards. L4 and L5 are dynamically stable, L1, L2, L3 require station keeping. The array provides continuous global phase coverage with geometric redundancy. Any three stations can reconstruct the full 6.8 GHz reference in the event of failure at any 2.2 BBG-SVG, buckyball stabilized superfluid vortex gyroscope. 2.2.1 Operating principle. The BBG-SVG exploits the topological quantization of circulation in superfluid HELIUM4. Below the lambda transition temperature T lambda equals 2.1768 K, the helium-4 order parameter psi equals psi e caret acquires a macroscopic phase theta whose gradient determines the superfluid velocity, Vs equals mhe nabla theta. The Onsager-Feynman quantization condition requires that the circulation around any closed path enclosing a vortex line be quantized. Kappa equals contour integral versus SDL equals n times h per meter he, n element of z. For n equals 1, kappa equals h per meter he equals 9.97 times 10 to the power of 8 square meter per second. The angular rotation rate of the containing vessel produces a Sagnac phase shift between the two counter-propagating paths of the superfluid order parameter, where A is the enclosed area of the Sagnac loop and omega is the angular velocity. For the BBG-SVG parameters, the geometric conversion factor is h equals 6.626 times 10 cubed to the power of 4, equals 1.011 times 10 to the power of 4 rad s per radian. With the QLAG supplied SQUID phase noise floor def equals 1 times 10 to the power of 9 rad, square root hc, the angular velocity noise floor is do equals 1.011 times 10 to the power of 4 times 1 times 10 to the power of 9 equals 1.011 times 10 cubed rad s, square root hc equals 3.47 times 10 degree deg, square root hour. 2.2.2 Fullerene vortex marker. A corrected ARW figure. The original provisional stated ARW equals 2 times 10 to the power of 8 deg, square root hour. The corrected value is 3.47 times 10 degree deg, square root hour, representing performance approximately 58 times better than originally stated. The error arose from an incorrect unit conversion. This correction strengthens the IP claim. 2.2.4 Critical velocity and dynamic range. The maximum sustainable 2.2.2 Fullerene vortex marker. A single C60 molecule is trapped in the vortex core by the Bernoulli pressure gradient. The relevant trapping mechanism is the Magnus force, not bulk thermodynamic entropy coupling as implied by the simple delta U equals S delta TV expression in the provisional. For a particle of radius in a vortex flow field, the Magnus force per unit depth is where versus ns is the superfluid normal fluid relative velocity and versus p is the particle velocity. For a C60 molecule at a counterflow velocity versus ns approximately equals 2 mm per second, the trapping well depth obtained by integrating the Magnus force over the core radius is in the range 10 squared minus 10 to the power of 8j, Berloff and Roberts, 2000. Sergeyev, Berengi and Kivitides. 2006, consistent with the filings claimed 5 times 10 squared j. The fullerene is thus stably trapped for timescales vastly exceeding the measurement cycle. And the spectroscopic solvation shell verification provides an in situ diagnostic without mechanical contact. 2.2.3 Second sound axial stabilization. Second sound, the entropy, temperature wave mode unique to superfluid helium, propagates at C2 approximately equals 20 meters per second at 1.8 Ka. Resonant cavity of length L equals 10 millimeters supports a fundamental standing wave at F1 equals C2 equals 1.0 kilohertz. The driven counterflow creates a periodic axial potential with trap frequency omega z, approximately equals 30 Hz and a 0-point positional uncertainty sigma z less than 10 nanometers. Because the confinement is provided by an acoustic wave rather than any mechanical element, there is no wear mechanism, no aging of the spring constant, and no friction contribution to long-term scale factor drift. Corrected ARW figure. The original provisional stated ARW equals 2 times 10 to the power of 8 deg square root. This correction strengthens the IP claim. 2.2.4 Critical velocity and dynamic range. The maximum sustainable rotation rate is set by the velocity at which the centrifugal force on the trapped fullerene exceeds the Magnus trapping force. The relevant length scale is the He2 healing length She approximately equals 0.6 nanometers at 1.8 K. Using the correct healing length, VC equals kappa equals 9.97 times 10 to the power of 8, approximately equals 26.5 meters per second, approximately equals 25 meters per second. Omega max equals versus C, R equals 26.5 divided by 0.005 equals 5,300 radians per second, approximately equals 3.04 times 10 to the power of 5 deg, s. The dynamic range omega max, do approximately equals 5,300, approximately equals 3 times 10 to the power of 15 sets the BBG-SVG as the only gyroscope technology capable of simultaneously tracking sidereal rotation and high agility maneuver without range switching or sensor handover. 2.3 MANSA, Multifunctional Adaptive Nanocarbon Surface Architecture. The MANSA skin integrates 4 functional layers into the vehicle surface. AC60 functionalized passivation matrix providing AL flux attenuation by 3 orders of magnitude. A gated graphene network with voltage tunable sheet resistance and adjustable IR emissivity. Graphene nanoribbon thermal spreaders with in-plane conductivity tilde 2000 W per meter K, and a gold on alumina coplanar waveguide. Network distributing the QLAG 6.8 GHz phase reference to all quantum instruments on the vehicle. The critical CPW phase distribution specification is 5 to 8 mRAD jitter over the full mission thermal envelope. This requires the GNR thermal router to maintain the CPW substrate within plus or minus 2 K of setpoint. Under this condition, the thermal expansion contribution to phase drift at 6.8 GHz is dF equals 2 pi times 6.8 times 10 to the power of 9 times, CF approximately equals 5 to 10 mRAD, consistent with the Filings stated specification. This is the assumption that must be made explicit in any peer-reviewed version. 2.4 DRGN-ELF. 2.4 DRGN-ELF, Differential Relativistic Geodesy Network with ELF coupling. The DRGN-ELF system is a ground-based geodetic network that combines 3 elements not previously combined in the prior art: borehole optical atomic clocks, cryogenic superfluid rotation subtraction via the BBG-SVG, and differential ELF waveguide phase as a real-time crustal strain correction channel. The system achieves sub-millimeter geopotential height resolution at sub-hourly cadence without dependence on optical fiber links or satellite uplinks. 3. Topological protection and the Kivelson framework. A central argument in both the BBG-SVG and DRGN-ELF disclosures is that the superfluid vortex gyroscope provides qualitatively superior long-term scale factor stability compared to classical gyroscopic technologies. This claim rests on a precise theoretical foundation in the modern theory of macroscopic quantum order, whose most rigorous development is found in the work of Professor Stephen Allen Kivelson. 3.1 The Kivelson Research Program. Kivelson's central contribution to condensed matter physics is the systematic investigation of how qualitatively new macroscopic behaviors emerge from strongly correlated quantum mechanical many-body systems. His canonical results include the theory of pneumatic Fermi fluids, the theory of pair-density wave superconductors in cuprates, Agderberg, Davis, Edkins, Fradkin, Kivelson et al. Annual Review of Condensed Matter Physics, Volume 11, 2020, and the General Framework for Identifying and Classifying Emergent Order in Interacting Electron and Boson Systems. The core theoretical claim, developed with greatest generality in the pair-density wave paper, is that when a many-body system develops macroscopic quantum coherence, the resulting order parameter field psi encodes topological quantum numbers, integer-valued invariants associated with the global topology of the order parameter manifold, that are protected against any local perturbation by an energy gap delta top. Local perturbations cannot continuously deform the topological invariant without paying an energy cost of order delta top. This is topological protection. 3.2 Application to the BBG-SVG vortex lattice. The superfluid vortex in the BBG-SVG is precisely the type of topologically protected excitation that Kivelson's framework describes. The superfluid order parameter psi equals psi e caret defines a U-order parameter manifold. The winding number of the phase field around the vortex core is. This integer winding number is the topological invariant. It cannot be changed by any local perturbation, thermal noise, vibration, electromagnetic interference, without a topological transition that requires nucleating a new vortex or annihilating the existing one. The energy barrier for such a transition is of order delta top approximately equals times lane approximately equals 10 squared to the power of 4j at 1.8 K for R equals 5 mm, Xi equals 0.6 nanometers. This is approximately 7 times 10 to the power of 4 times kBt at the operating temperature of 1.8 K, a barrier so large that spontaneous vortex nucleation by thermal fluctuation is astronomically unlikely on any engineering timescale. By direct analogy with Kivelson's treatment of fractional quantum Hall states and PDW superconductors, the rotation-encoded Sagnac phase is not merely reduced by lower thermal noise, it is topologically frozen. This is a qualitative distinction, not a quantitative improvement, over any classical gyroscope technology. The practical consequence for the QSN is that the BBG-SVG does not drift. Its scale factor, the coefficient relating measured phase to physical rotation rate, is determined by fundamental constants rather than by material properties or alignment, both of which age. Scale factor stability governed by fundamental constants rather than material aging is the enabling property for the multi-year autonomous deep space and geodetic missions that QSN targets. 3.3 Kivelson's framework extended, emergent order as engineering principle. A further insight from Kivelson's program is that the robustness of macroscopic quantum order against disorder is a generic property of condensed phases with broken continuous symmetries, not a special feature of any particular material. For the QSN, this implies a broader design principle. Wherever a continuous physical measurement can be encoded as the topological invariant of a macroscopic quantum state, that measurement inherits topological protection and is therefore qualitatively more suitable as a long-term reference than any classical analog. The BBG-SVG vortex rotation sensor is the first application of this principle to navigation-grade inertial sensing. The QSN represents the first application at planetary scale. 4. DRGN-ELF, the Seeley geodetic equation. 4.1 Chronometric leveling foundation. General relativity predicts that clocks at different gravitational potentials tick at different rates. For two clocks at positions xi and xj in the Earth's combined gravitational and centrifugal potential U, the proper frequency ratio is where delta Uij equals U minus U is the geopotential difference and F0 is the nominal clock transition frequency. At fractional frequency uncertainty delta F, F0 approximately equals 5 times 10 to the power of 8, the equivalent height resolution is delta H equals delta Fc squared, approximately equals 0.5 centimeters. This already surpasses spirit leveling over baselines exceeding 100 kilometers. 4.2 Sagnac correction, dimensionally consistent form. For a clock comparison over a baseline with time-varying differential rotation do equals omega I minus omega j, the relativistic Sagnac effect contributes a fractional frequency bias. The correct form, derived from the post-Newtonian metric and expressed as a dimensionless ratio, is where r is the position vector of the midpoint of the transfer link and versus link is the link's propagation velocity vector. The integrand do times has dimensions, divided by c squared the result is dimensionless in radians, as required. The corrected form makes versus L in the provisionals expression explicit as the cross product r times v link. 4.3 ELF crustal correction term. The electrokinetic effect converts pore fluid motion driven by crustal stress into a bulk electromagnetic current density J equals alpha E nabla P pore, where alpha E is the site-specific electrokinetic coupling coefficient and P pore is the pore fluid pressure. This current excites ELF radiation in the 3 to 300 Hz band that propagates globally in the Earth ionosphere waveguide with attenuation approximately 0.25 decibels per megameter at 15 Hz. The differential ELF phase between receivers at sites I and J encodes the path-integrated conductivity contrast, where beta is the real part of the waveguide propagation constant and psi src is the source phase. The ELF-derived crustal strain correction is where eta is the empirically calibrated electrokinetic coupling coefficient and kd is the dominant ELF wave number. The coefficient eta must be determined during a calibration campaign combining co-located seismic, deformation, and ELF monitoring. It is site-specific but temporally stable over periods of months to years. 4.4 The Seeley geodetic equation, canonical form. Combining the three terms above and solving for the geopotential difference, the canonical form of the SGE is 4.5 Error budget. 5. The quantum state network, architecture. 5.1 Foundational principle. Physical systems are not collections of independent objects. They are coupled dynamical states evolving under shared governing equations. The fragmented sensing architecture of current civilization estimates projections of a common underlying state psi, the total observable physical state of the Earth system, onto narrow measurement subspaces. The result is a collection of partial estimates that are mutually consistent only approximately and sporadically. The QSN is defined by its objective, continuous, phase-coherent estimation of the full planetary state vector psi such that psi approximately equals psi subject to observational uncertainty. This is a well-posed estimation problem, and the tools of modern state estimation theory, the extended, unscented Kalman filter, particle methods, variational data assimilation, provide a rigorous framework for its solution provided the state space formulation, observation model, and noise statistics are properly specified. 5.2 State space formulation. The full planetary state vector is partitioned into 7 sub-state domains. Psi equals IP claim, Seeley geodetic equation. The measurement equation above. Combining chronometric leveling, dimensionally consistent cryogenic Sagnac correction via BBG-SVG, and ELF electrokinetic crustal strain compensation, is the sole and independent intellectual contribution of Chris D. Seeley, first publicly disclosed in the DRGN-ELF provisional and corrected and canonicalized herein. Priority date, May 2026. Where G equals gravitational state, geopotential field U, mass distribution ρ, tidal forcing. Parameterized on a spherical harmonic basis to degree, order ng. A equals atmospheric state, pressure P, temperature T, humidity Q, winds V. Current NWP models operate at Na approximately 10 to the power of 6 minus 10 to the power of 9 degrees of freedom. O equals ocean state, sea surface height, temperature, salinity, current fields. NO approximately 10 to the power of 7. M equals magnetospheric, ionospheric state, electron density Ne, magnetic field B, geomagnetic index Kp. Nm approximately 10 to the power of 5. I equals infrastructure state, strain, displacement, and load state of monitored structures and networks. Ni scales with deployment density. E equals electromagnetic state, ELF, VLF, HF field amplitudes, Schumann resonance mode excitation. Ne approximately 10 to the power of 3. S equals space environment state, solar wind parameters, SEP flux, orbital conjunction catalog. Ns approximately 10 to the power of 4. The total state dimension N total equals Ng plus Na plus No plus Nm plus Ni plus Ne plus Ns is dominated by Na at current operational resolutions. But the geodetic and electromagnetic substates are those for which the QSN hardware provides unique new observables not available from existing sensor networks. 5.3 Measurement hierarchy and sensor fusion. QSN sensor inputs are organized into 5 layers, each contributing a phase-coherent measurement vector Yk. Each layer provides a measurement vector Yk at its native cadence. The QSN fusion engine operates a hierarchical estimation scheme. High-rate sensors drive the inertial navigation filter, medium-rate sensors drive the geodetic estimation filter, low-rate sensors drive the mass transport and atmospheric filters. The outputs of lower frequency filters are passed as prior constraints to higher frequency filters, creating a consistent multi-timescale state estimate. 5.4 Recursive state update. The QSN state update takes the form of a generalized nonlinear filter. The state evolution equation is where F is the coupled Earth system forward model, UK is the known forcing vector, and WK is the process noise with covariance QK. The measurement update is where H is the forward observation operator mapping state to observable, and KK is the Kalman gain matrix. With PK the state error covariance and RK the measurement noise covariance. For the nonlinear Earth system model, F and H are implemented as the unscented transform or ensemble Kalman to propagate the covariance without linearization artifacts. For the high-dimensional substates, variational 4D VAR assimilation replaces the explicit Kalman update to avoid the O covariance inversion cost. 5.5 Information theoretic capacity and observability. The QSN's information gathering capacity from N sensors with bandwidths BI and signal-to-noise ratios SNRI is bounded by the Shannon channel capacity. It is important to distinguish this from the observability of the state psi. Observability is the question of whether the state can be reconstructed from the measurements, and is governed by the Fisher information matrix. The state is observable if and only if F is full rank, i.e., no eigenvalue of F is 0. Practical observability requires that all eigenvalues of F exceed a threshold lambda min set by the required estimation accuracy. The superlinear value of integrating additional sensors, expressed qualitatively in the QSN concept node as O proportional n caret alpha with 1 less than alpha less than 2, arises from the structure of F. Adding a sensor with an observation function Hi not aligned with the existing null space of F provides greater than proportional improvement in the worst-case eigenvalue of F, thereby extending observability to previously unobservable state directions. A formal proof requires specification of the observation geometry, which is site deployment dependent and constitutes a recommended topic for Phase 1 experimental studies. 5.6 Predictive Earth Model. Once the current state estimate psi has converged, it can be propagated forward by the geophysical forward model F. Delta T equals F caret, plus or minus, forecast uncertainty growing with delta. Forecast applications include seismic hazard from detected SSE evolution, infrastructure degradation from monitored strain accumulation, weather prediction from assimilated geopotential and mass loading data, power grid stability from geomagnetic storm prediction, orbital conjunction analysis from assimilated space environment state. The forecast horizon for each substate is limited by the Lyapunov exponents of the corresponding dynamical system. Atmospheric predictability is fundamentally limited to approximately 2 weeks. Crustal deformation forecasts are useful on months to years timescales. Space environment forecasts depend critically on solar wind lead time. 6. Priority applications. 6.1 Slow slip event detection and seismic hazard. SSEs are quasi-seismic fault creep episodes that accumulate and transfer strain without generating strong seismic radiation. They are epidemiologically correlated with large megathrust earthquake initiation but are currently detected only when they are large enough or long enough to be visible in GNSS time series. The DRGN-ELF network closes this detection gap. The SGE resolves geopotential changes equivalent to 0.7 mm height at 1 hour cadence, detecting SSEs 4 times smaller and 24 times faster than current GNSS networks. The ELF electrokinetic channel provides an independent less than 1 minute alert when poor fluid pressurization precedes or accompanies the slip, potentially extending warning times for triggered seismicity by tens of minutes. 6.2 Hydrological and cryospheric mass transport. Continental water storage changes impose geopotential perturbations of up to tens of centimeters in height equivalent at weekly to annual timescales. Gyroscope resolves these at 300 km spatial resolution and 30-day cadence, insufficient for monitoring localized groundwater depletion, permafrost active layer drainage, or ice sheet calving events. The DRGN-ELF network fills this gap at less than 10 km resolution and sub-daily cadence, enabling operational management of water resources and real-time tracking of ice sheet mass loss relevant to sea level projections. 6.3 GPS denied and contested navigation. The BBG-SVG, QLAG combination provides autonomous inertial navigation without any dependence on external satellite systems. With the corrected ARW of 3.5 times 10 degree deg square root hour, the accumulated attitude error over a 30-day mission is approximately 4.3 times 10 to the power of 8 deg, essentially 0. Position error accumulates as the double integral of acceleration measurement error, with the BBG-SVG bias of less than 10 to the power of 9 deg per hour. The dead reckoning position error remains below 1 meter over 30 days for a vehicle with known initial conditions. This capability is directly applicable to submarine navigation, polar and high-latitude operations where GNSS coverage degrades, deep space missions beyond GPS coverage, and contested environments where GNSS is jammed or spoofed. 6.4 IHRF densification and sea level reference. The International Height Reference Frame requires geopotential numbers at reference stations globally to 10 square meter per square second accuracy. Non-fiber sites, mid-ocean islands, polar stations, active volcanoes cannot currently be tied to the IHRF at this accuracy. DRGN-ELF, using the ELF waveguide as its transfer channel rather than optical fiber, extends chronometric leveling to any location on Earth accessible by borehole drilling, enabling a globally consistent physical height reference for sea level and ice sheet change monitoring. 6.5 Fundamental physics. The QSN sensing stack enables several fundamental physics measurements inaccessible to existing networks. The QLAGL-1L5 maser array provides continuous monitoring of the gravitational redshift across the Sun-Earth system, enabling tests of the equivalence principle at 10 squared precision. The BBG-SVG, when deployed in a geodynamically active region, can measure frame dragging from the Earth's rotation at the level of approximately 7 NRAD per year, a fundamental GR observable accessible for the first time with a ground-based instrument. The DRGN-ELF phase network provides a continuous global monitor of the Earth's normal mode-free oscillations, complementing seismic networks with an electromagnetic observable sensitive to mass redistribution rather than ground motion. 7. Inventorship, IP claims, and relationship between disclosures. 7.1 Hardware Subsystems, Joint IP. The following subsystems are jointly invented by Chris D. Seeley and Brad Yoakum and filed as joint provisional patents in May 2026. Their inventorship is not altered by this document. QLAG, Quantum Lagrange Array Gravitational Interferometer, Beck-Maser Station Design, Lagrange Point Deployment Architecture, Parametric Transducer H-int, and 6.8 GHz frequency distribution. BBG-SVG, Buckyball Stabilized Superfluid Vortex Gyroscope, Single Vortex He2 Loop, C60 Fullerene Marker and Helium Droplet Pickup, Second Sound Axial Resonator, Josephson Weaklink and DC Squid Readout, Phase Lock to QLAG. MANSA, Multifunctional Adaptive Nanocarbon Surface Architecture, C60 Passivation Layer, Gated Graphene Network, GNR Thermal Router, O on Illumina CPW Sublayer, and Vehicle Integration Addendum. 7.2 Geodetic and Architecture Contributions, Sole IP. IP Claim 1, Seeley Geodetic Equation. The dimensionally consistent measurement equation combining chronometric leveling, cryogenic Sagnac correction via BBG-SVG, and ELF electrokinetic crustal strain correction is formalized in Section 4.4 of this document. Priority, May 2026. Inventor, Chris D. Seeley. IP Claim 2, ELF-mediated geopotential coupling modality. The use of differential ELF waveguide phase measurements as a real-time crustal strain correction term in a chronometric geodesy network, enabling geopotential recovery independent of fiber or satellite uplink. Priority, May 2026. Inventor, Chris D. Seeley. IP Claim 3, DRGN-ELF network topology. The three-tier architecture integrated by the SGE. Priority, May 2026. Inventor, Chris D. Seeley. IP Claim 4, Electrokinetic ELF Calibration Protocol. The methodology for empirical determination of the site-specific eta coefficient via concurrent ELF, seismic, and clock comparison campaigns, and its use as a real-time SGE correction coefficient. Priority, May 2026. Inventor, Chris D. Seeley. IP Claim 5, QSN State Space Architecture. The planetary state vector formulation psi equals, the 5-layer sensor fusion hierarchy, the recursive state update architecture, and the Fisher information observability criterion applied to the QSN sensor network. Priority, June 2026. Inventor, Chris D. Seeley. IP Claim 6, Kivelson Framework Justification for Topological Sensor Superiority. The application of the topological winding number protection argument to justify the qualitative superiority of superfluid vortex gyroscopes as long-term inertial references in geodetic and planetary state estimation applications. Priority, May 2026. Inventor, Chris D. Seeley. 8. Development Roadmap. The QSN development roadmap comprises 5 phases, each technically and commercially self-justifying, with each phase enabling the next. The roadmap addresses the critical technology bottlenecks identified in the comparative prior art analysis. The Fullerene vortex loading problem, the absence of a regional scale QLAG equivalent frequency backbone, and the ELF calibration program required before DRGN-ELF delivers operationally certified geopotential data. The near-term critical path is not Lagrange point infrastructure but the QLAG light regional relay concept. A LEO or stratospheric node carrying a compact optical lattice clock and a MANSA CPW panel, locking to ground clocks via demonstrated free space optical frequency. Transfer and rebroadcasting a coherent 6.8 GHz tone to regional BBG-SVG users. This is the infrastructure bridge that makes BBG-SVG navigation useful before the full QLAG Lagrange array is deployed. 9. Conclusions. This paper has accomplished 4 objectives. 1. Identified and corrected 5 technical inconsistencies in the prior provisional filings, in each case. Demonstrating that the physical claims and performance targets are correct or conservative once the notation and derivation pathway are properly specified. 2. presented a consolidated, peer-review-ready description of the QSN architecture. The state space formulation, the 5-layer sensor fusion hierarchy, the recursive state update in its UKF, NKF form, the information theoretic capacity bounds, and the Fisher information observability criterion. 3. Provided the canonical, dimensionally consistent form of the Seeley geodetic equation and established its role as the measurement nucleus of the DRGN-ELF system and of the G-domain estimation layer within the QSN. 4. Established the Kivelson topological protection argument in its precise form, the quantized vortex winding number. The topological energy barrier delta top approximately equals 7 × 10 to the power of 4 kBt at operating conditions. And the resulting qualitative distinction between a topologically frozen scale factor and a thermally noisy one, as the rigorous justification for the BBG-SVG's fitness as the rotation reference in a century-scale planetary sensing network. The QSN is not an incremental improvement to existing sensing infrastructure. It is a new layer of physical reality representation, the first architecture designed from the outset to estimate the total physical state of the Earth system as a single coherent dynamical object. At the phase coherence level enabled by topologically protected quantum sensors. The intellectual framework, architecture, and IP priority are established herein under the primary inventorship of Chris D. Seeley. References: Agterberg, D.F., Davis, J., Edkins, S.D., Fradkin, E., Van Harlingen, D.J., Kivelson, S.A., Lee, P.A., Radzahovsky, L., Tranquita, J.M., and Wang, Y. The Physics of Pair Density Waves, Cuprate Superconductors and Beyond. Annual Review of Condensed Matter Physics, 11, 231-270. Berloff, N.G., and Roberts, Ph. Motions in a Bose condensate, Ix. Crow instability of antiparallel vortex pairs. Journal of Physics A, Mathematical and General, 34, 81. Birhamar, A. On a Relativistic Geodesy. Bulletin Geodesic, 59, 207-220. D. H. Fu, C. Zhang, J. and Huang, Q. Numerical study of global ELF electromagnetic wave propagation with respect to lithosphere-atmosphere ionosphere coupling. Remote Sensing, 13, 4107. Fradkin, E., and Kivelson, S.A. Pneumatic Fermi Fluids in Condensed Matter Physics. Annual Review of Condensed Matter Physics, 1, 153-178. Grati, J., Collar, S., Vogt, S., et al. Geodesy and Metrology with a Transportable Optical Clock. Nature Physics, 14, 437-441. Kivelson, S.A. https:// Kivelson, S.A. Prabhu Goel Family Professor of Physics, Stanford University. Research Program: Emergent Properties of Strongly Correlated Quantum Mechanical Many-Body Systems. https:// Costantino, G., Gifford Rowason, S., Radige, M., et al. Slow Slip Detection with Deep Learning in Multi-Station Raw Geodetic Time Series. Archive, 2305.19720. Liu, D.X., et al. Measuring Intercontinental Scale Geopotential Difference using Atomic Clock Frequency Comparison with PPP Technique. Science Direct. Melchtabler, T., Grosch, G., Lisdat, C., Schmidt, P.O., and Denker, H. Atomic Clocks for Geodesy. Reports on Progress in Physics, 81, 064401. Obara, K., and Cato, A. Connecting Slow Earthquakes to Huge Earthquakes. Science, 353, 253-257. Packard, R.E., and Vitali, S. Principles of Superfluid Helium Gyroscopes. Physical Review B, 46, 3540. Seeley, C.D., and Yoakum, B. QLAG Lagrange Point Maser Network, BBG-SVG Superfluid Vortex Gyroscope, and MANSA Adaptive Nanocarbon Surface Architecture. Provisional Patent Filings, May 2026. Sealy, CD. DRGN-ELF, Differential Relativistic Geodesy Network with extremely low-frequency crustal coupling. Provisional Disclosure, May 2026. Sealy, CD. QSN, Quantum State Network, a Planetary Phase-Coherent State Architecture. Concept Disclosure, June 2026. Sergeyev, Y.A., Berengi, C.F., and Kivitides, D. Motion of micron-size particles in turbulent helium-2. Physical Review B. 74, 184506. Takano, T., Takamota, M., Ushijima, I., et al. Geopotential measurements with synchronously linked optical lattice clocks. Nature Photonics, 10, 662-666. Velikov, E.P., et al. Controlled Source ELF Method. Geoelectromagnetics Research Institute. Inventorship Affirmation and IP Notice. Chris D. Sealy, June 2026. Inventorship Statement. The QLAG, BBG-SVG, and MANSA hardware technologies are jointly invented by Chris D. Sealy and Brad Yoakum. This document does not alter their inventorship. The following are the sole and independent intellectual contributions of Chris D. Sealy. The Sealy geodetic equation in its canonical, dimensionally consistent form. The DRGN-ELF three-tier network topology, ELF geopotential coupling modality, and electrokinetic calibration protocol. The QSN state-space architecture, 5-layer sensor fusion hierarchy, recursive state update formulation, and Fisher observability criterion. Application of the Kivelson topological order framework to justify the qualitative superiority of superfluid vortex gyroscopes in planetary sensing. The 5-phase QSN development roadmap and the QLAG Light Regional Relay concept as the critical path bridging technology. This document constitutes a public prior art disclosure establishing priority dates of May to June 2026 for patent applications on the above inventions to be filed in the name of Chris D. Sealy. All rights reserved. No license, express or implied, is granted to any party by reason of this publication. Chris D. Sealy, June 2026. Inventorship Statement. The QLAG